Hello friends, in this video I'm going to be solving questions about non-equilibrium, and I will be repeating myself again and again. If a system is in equilibrium, total force is zero, and in non-equilibrium the system is moving in a direction and total force will not be zero. So examples of non-equilibrium. The questions will be very similar to the examples of equilibrium, except now we will have an acceleration and force, and we'll be calculating acceleration, again looking at total force is equal to m total times a. Except now it is not equal to zero. Now in the questions I cannot say the total force in one direction are equal to total force in the other direction, and it will be changing everything. Is it very complicated? No, it's very, very similar. So first example is we have two blocks. We solved question involving blocks already. That was already a non-equilibrium question. We had a force pushing the blocks, very similar to here. So we already know non-equilibrium. We solved some simple and harder questions. This one is very similar, only we are now involving the friction that we learned about it. Since we learned about it. So we have M1, M2, and they're pushed by a force, and there is a friction on the surface. Let me read the question. Two blocks are placed on a horizontal surface with a coefficient of friction, kinetic friction, 0.25. So the question says mu K is 0.25, coefficient of kinetic friction. The masses are M1 3 kilogram and M2 is 2 kilograms. So I'm putting down my known values. M1 is 3 kilogram and M2 is 2 kilogram. A, if a horizontal force of F 18 Newton is applied to the blocks, what is the acceleration of the system? So part A of this question says if F is equal to 18 Newton, we have friction, and system is moving to the right. Intuitively, you can decide this in here. Friction cannot move the system, so if there is a force, if there is a motion, it should be due to this force. So this is the direction of motion. System is accelerating. Acceleration will be in the same direction of force. Let me put that as well. And I'm choosing the direction of motion to be positive. So my positive direction in this question is the direction of total force, acceleration. So the direction of motion is the same direction as the direction of total force, and this is my positive direction of choice. The other direction will be negative. So to the left, we have negative. A is asking me if F is 18 Newton, what is the acceleration of the system? We solved a question involving even three masses, only there was not a friction in there. And we learned that if a system is moving together, all the masses, all the objects in the system will have the same acceleration. So for the system, I can write down total F is equal to M total times A and get acceleration. But now in this question, we're going to have frictional forces, kinetic frictional forces. Applied on M1, which we will call FK1, kinetic friction force 1, and applied on M2, FK2. And the frictional forces will always be opposing to the motion. So now I'm writing down total F is equal to M total times A. And I'm writing my total forces. I'm jumping to magnitudes again. In positive direction, I have F. Negative direction, I have Fk, so Fk1 and Fk2. So I have F minus Fk1 minus Fk2 is equal to M total, M1 plus M2 times A. And I assume and hope that you all now can see that Fk1 and Fk2 are negative in the direction of my choice, that is negative. and F is in the positive direction. As I am writing down my total F, it's F minus Fk1 minus Fk2 is equal to M total, M1 plus M2 in this case, times A. And from here we're going to calculate our A value. I can solve for A directly, dividing each side by M1 plus M2, leaving A alone. A will be equal to F minus Fk1 minus Fk2 divided by M1 plus M2. Now all we're left to do is to find these values. We know F already, let's find Fk1 and Fk2 in here and enter them in there to get A. Fk1 will be M1 G mu K, Fk2 will be M2 G mu K. Let me remind you again, kinetic frictional force is always equal to kinetic frictional coefficient mu K times the normal force to the surface we're talking about. And over here, let me use green so it will be distinguished. We have downward direction M2G, gravitational force, and M1G. So the normal forces in this part of the surface will be equal to M1G. We call this N1. And normal force applied on M2 will be equal to M2G. Again, the normal force is the force perpendicular to the surface, and it's a reaction force that against the forces that are applied to the surface. So only action force on this surface by M2 is M2G, and N2 will be equal to M2G. Let me put these here actually. I'm going to delete this and tell everything. So first we find M1 and M2. And 1 is equal to M1G, normal force on M1, and M2 is equal to M2G, normal force on M2. And Fk1 will be mu K times N1, and we got N1, normal force, mu K times M1G. Fk2, small f, frictional force on M2, kinetic frictional force is equal to mu K times N2, mu K, N2 is equal to M2G, M2G. And let's now put the values. We had mu K 0.25 times M1 3 kilogram times G 9.8 meters per second squared. I'll get a value of Newton in here. Let me see if I have it in here calculated separately. No, actually, I'll calculate it for you. So we have 0.25 times 3 times 9.8, 7.35. 7.35 Newton. For Fk2, we have M2G mu K, so it will be 0.25 again. M2 is 2 kilogram times 9.8 meters per second squared. And again, as a reminder, mu K will never have a unit, unitless, and it's always smaller than 1. So 0.25 times 2 times 9.8. It's equal to 19.85. There is a mistake. Okay, let me check that. Edit them out, I guess. 3.25 times 2 times 9.8, 4.9. We calculated the trick on me, sorry about that. So this is 4.9. So Fk1 is 7.3 Newton, Fk2 is 4.9 Newton. I guess first one was also erroneous. Let me check that. 0.25. I punched something wrong, I guess. Times 9.8. Okay, good. Alright, correct. So now that I have these values, I know F, I know M1, M2, I can put everything in place. A will be equal to, I'll carry it a little bit here, so it will be separate. F, 18 Newton, I believe, minus Fk1, 7.35 Newton, minus Fk2, 4.9 Newton, divided by M1 plus M2, 3 kilograms plus 2 kilograms. And from here I should get an answer as A, 1.15 meters per second squared. Again and again, please do the same calculations, check my answer. This will be a practice for you. You'll also be checking if I made a mistake in here, an arithmetical mistake. And you can correct me. So this is the logic. We have force pushing to the right, there's a motion, acceleration. So if the system is accelerating, acceleration is in the same direction as the total force. And we choose the direction of total force, which is the direction of motion here, to be positive. The other direction is negative. And to find the A, acceleration of the system, we say F total is equal to M total times A. And F total is F minus Fk1 minus Fk2. Fk1, Fk2 being the frictional forces acted on M1 and M2 by the surface. And this is equal to M total times A, which is M1 plus M2 times A. We solve for A from here as total force divided by total mass. And then we calculated over here, let me divide this part, what Fk1 and Fk2 are. As calculating the frictional force, kinetic frictional force, we say always equal to the kinetic frictional coefficient times the normal to the surface. And normal to the surface at M2 point, so the normal force is acted on M2 is equal to M2g. And normal force acted on M1 is equal to M1g. To find a normal force, again, we look at the forces that are applied to the surface perpendicularly, and normal force is equal in magnitude, opposite in direction to the total of these forces. Reaction force by the surface symbol. So we got all values put in here. Mu k M1g is Fk1, and mu k M2g is Fk2. Got the values and if them entered in the equation we got for A, and got A as 1.15 meters per second squared. Let's go into part B of this question. I'm gonna have to delete this. Let us write down the values we got for frictions in case we will need them. We got Fk1 to be 7.35 Newton and Fk2 to be 4.9 Newton. Let me delete the rest so we'll have some space in here. Oops, sorry about the phone. It's with me too. I deleted the figure. Okay. So let me draw the figure again. We have M1, M2, and we have frictional forces. Maybe I'll remove MG, M2G, M1G, Fk1, Fk2, and we know the values of Fk1 and Fk2 now. So the part A was asking me about acceleration. Let's see part B. What part B is asking? The force acted on M2 by M1. So what is the force acted on M2? This is M2, by the way, by M1. For this, we solved many questions. In the frictionless case, this will be the same, simple. We'll be dividing the masses into two parts and looking at them separately, calculating the values we need to calculate. Let's divide both masses, because in part C we'll be solving for M1 as well. So here's our different masses. This is M2, this is M1, and let's put the values we already know. We have F acted on M1, and it's equal to 18 Newton. We have calculated kinetic frictional force acting on M1. To the left, FK1, 7.35 Newton. We also have a frictional force acted on M2, FK2, small f, 4.9 Newton. Now we're going to find the force acting on M2 by M1. Let's call this F2. I'm going to use black here. F2 force. That's what we're trying to find. And if M2 is acting on M1 is acting on M2 by F2, M2 will be shown a reaction force opposite in direction, equal in magnitude. So M1 will be also acted by the same force, F2. Magnitude I'm showing here. Direction is negative. Because the direction of positive direction for us in this question was this way, to the right, we'll stick with this to get correct answers. So here let's put the directions as well. Just beside the forces we have positive F2 and negative F2 here. F is positive and all the frictional forces are negative. What else we also know is the acceleration of the system to the right. Let's put it in here. 1.15 meters per second squared. I forgot to write it down. Let me check what it was again. So we want to, yes, 1.15 meters per second squared. Now can I easily find F2 by separating M2 using A, which is equal to A2. So this A goes for all the masses in the system. A1 and A2 are all equal to the acceleration of the system. That's 1.15 meters per second squared. So let's find it. For M2 only, let's use the color. For M2, I'm writing a total force, total F2. Oh, let's not be very too scientific here, so I won't confuse you. We have the total forces F2. I'm going to put it directly. And opposite direction, I have minus FK2. This is equal to M2A. So we jumped in the total force for M2 is equal to M2A. It's the same thing. Total force is equal to M total times A. I'm applying it to mass 2 now. So we have F2 positive direction minus FK2 is equal to M2A. And this will give me the value of F2 because I know FK2, I know M2, I know A. So F2 applied on mass M2 is equal to M2 times A plus FK2, kinetic friction force 2. Let's put the values. F2 is equal to 2 kilogram times A, 1.15 meters per second squared, plus FK2, 4.9 Newton. And from here we'll get a value for F2, which is equal to 7.2 Newton. Please check the answers again. It will be a practice for you, and you'll be checking if I have any calculation mistakes there. So this is B. B is asking us what is F2. And we solved it in here. I'm going to leave this figure now. We're going to solve the total force for M1. So I think that's what C was asking. What is the total force is acting on the 3 kilogram block? So yes, C is asking us what is the total force on M1. Only we have all the forces we needed for M1. We know FK1, we know F, and we calculated F2 just in here, so we know all the forces acted on it. We'll be just calculating what is it in total magnitude. So let's see in here, total force on M1. My positive direction is the same. I'm just going to calculate what is the total force, which should be in the direction of motion, accelerated motion, and I'm writing down all the forces. I could call this total F1, but I'm not going to, so we are just going to jump and do it. F, positive direction, minus FK1, negative direction, and F2 is applying on M1 in negative direction as well, so it will be minus F2. And this is the total forces acted on M1. This would be equal to M1 times A. So I can just jump in here. I know M1, I know A. I can just directly calculate total force acted on M1 using the simpler way, actually. If you're asked in an exam, you can do that. But I want to show you that they are the same thing. So F1 is 18 Newton. Minus FK1, 7.35 Newton. Minus F2, 7.2 Newton, is equal to 3 kilograms times 1.15 meters per second squared. And all these should give me as a total force, let's see here, 3.45 Newton. So this is the total force acting on M1. Please do the calculations and make sure they are correct. So this is one example of non-equilibrium. Now I'm moving on to another example which is simpler, but it gives us a good idea of how we should deal with some pulleys questions that are not in equilibrium. So the example 2 has a pulley system and two masses hanging from a pulley. And one mass in here, one mass on the other side. Let me see who's M1, who's M2. So we have M1 on the left and M2 on the right. And let's say we don't know which mass is what. And we're gonna see different situations. What happens if, for example, A is asking us in this figure. So in the figure we have two masses hanging at the end of string. Assume the pulley is frictionless, which is important, so there's no friction in here. We're not considering frictional force in there. And both the pulley and the rope are massless, which is also important. But this will always be the case for our questions, so we will not worry about friction on the pulley or mass of the spring. A, describe the motion if M1 is smaller than M2. Let's describe it. A, if M1 is smaller than M2, what would be the motion of the system? So what the forces we have in the system is on the right M2G, on the left M1G. What these two forces are doing is to take over each other, each one trying to move the other one in its direction. So we have M2G pulling to the right. If we look at the pulley, rotation of the pulley, which helps us understand the motion better than here, M2G is trying to pull to the right rotation and M1G is trying to pull to the left rotation. Now, if M1 is smaller than M2, then M1G will be smaller than M2G. And M2G will win in here. What the system will be doing is moving in this direction. And in these type of questions, what we're going to choose to be positive direction will be this. We're going to put it in here because the direction of motion to the right, rotating to the right, will be positive here. This direction is positive. And then this direction here will be negative. And using these, we're going to solve the values that we need to find. Will the system be accelerated? Yes. Acceleration will be bigger than 0. Because M2 is larger than M1, we have a larger force pulling in this direction, and we'll have the total force as this minus that, so M2G minus, so F total here will be M2G, m2g minus m1g. And this will be pulling system to this direction, and it will give us an acceleration as m1 plus m2 times a. So the idea is the same. We have a total force, we have acceleration if there's a total force larger than 0, and the system will be moving in the direction of the larger force. So if m1 is smaller than m2, that's what we're going to see. The system will be accelerating towards the direction of m2g pull, so m1 will be going up with the same acceleration, and m2 will be going down. System will be accelerated. I'm going to ask you to think about what happens if m1 larger than m2. And this will help you understand your situation better. And I'm going to jump on to C, where we're asked what happens if m1 is equal to m2. So if they're equal to each other, we'll be having two equal forces pulling in the same direction, right? So we have now m1g is equal to m2g. If I look at the total force, pick a direction. I could pick any now because there won't be any total force. So let's say F total. Let's pick the same direction as possible in this direction. So it will be m2g minus m1g, and it will be equal to 0. And this means acceleration will be equal to 0. What would happen in this system is that either it will stay stationary if nobody touches it, or if you give it one small initial velocity, it will be moving with this velocity, constant velocity, 0 acceleration. So if I push this to the direction of m2g, it will be moving in the direction of m2g with a constant acceleration in the case of m1 is equal to m2. If I push it in the opposite direction, the direction of m1g, then it will be moving in the direction of m1g. 0 acceleration, constant velocity. If I don't touch it, it will be stationary. So this is a nice example showing, helping us understand different situations. In the exams, I wouldn't like to ask you a question of this sort. The question would be involving either one of these cases. M1 is smaller, M1 is larger, or the masses are equal to each other. This was just to teach you how it works. All right, one more question, then we're out of here. This question is dealing with pulleys plus inclined planes. Is it too complicated? No. Plus we will have friction there. But then if I ask you the most complicated question in an exam or in an assignment, this would be one example. So let's solve this one too, and then we're done. And we're simply done with the questions I want to solve about equilibrium, non-equilibrium. The rest we'll be doing in the class. I'll be giving you some more examples of pulleys, inclined planes. We'll be doing some elevated examples tomorrow. So let's look at this question as the last example. Example 3. So we have an incline. It has a 30-degree angle here. And we have a mass on the incline, M1. I can take this one. So this is mass M1. We have a pulley attached to the incline and a rope coming in this way, and another mass on the right, called M2. It says M1 is 8 kilograms, so M1 is 8 kilograms in here. I'm not going to put it on the figures, it will be too messy otherwise. And M2 is, let's see, 22 kilograms. Let me read the question. Block 1 with M1 8 kg is moving on a 30-degree incline. This block is connected to another block with mass 22 kilogram by a massless cord that passes over a massless and frictionless pulley. So we don't, again, care about the mass of the cord, friction of pulley. I might as well not tell you about those, but to be correct, scientifically correct, I should. So we don't care about mass of the rope or the pulley or friction in between the rope and the pulley. A, find the acceleration of each block and tension in the cord if incline is frictionless. So part A says if incline is frictionless, there's no friction on the incline either, find acceleration of the system and tension in the cord. Acceleration and tension. Alright, so let's now look at the forces that are pulling us in each direction. And in here, I'm going to tell you the direction of motion, but if it is not told us, we can find it. We'll put down the forces. We'll have M2G in here, pull in this direction. I'm going to show two directions here. There are two possible directions of motion. Either the pulley will be rotating in this direction, M2G is larger and pulling in this direction, and M1 is pulling up, or the pulley is rotating in the opposite direction, and one is moving down on the incline and M2G is moving up. So we're going to find the direction by looking at the forces in opposite directions, but here it's kind of obvious. We have 8 kilogram M1 and M2 is 22 kilogram. This side will be larger. So the system will be moving in this direction, which I'm going to choose as positive here, and M1 will be moving in this direction, upward direction. So this direction here will be choosing a rotational direction kind of in here. The system is moving in this rotational direction is positive. For M1, the positive direction will be this. Total force will be in this direction. And acceleration will be in this direction for M1. And for M2, acceleration is downward. And the positive direction is the direction of acceleration. Again, we kind of have rotational direction here. Everything in this type of is moving the system in this direction. Rotational direction will be taken as positive. So I define the positive direction for M1 using this rotation over here, and positive direction for M2. And now I'm going to find all the forces applied on the system. There will be a tension force pulling M1 in here. And there will be a tension force pulling M2 upward in here. And this tension force, these two tension forces are the same because they are along the same rope. Along the same rope, we always have the same tension. We have Mg in there, M1G. And we have its components. We have component along the incline, as always, M1G sine the angle of incline 30. And here we have M1G cosine 30. If there's no friction, the cosine 30 is not effective. There is an action on the surface. There's a normal as reaction to this action, and that's all. We're done. If there is a friction on the surface, it will change. But this is all the forces we have in the system. M1G, M2G, components of M1G, M1G sine 30 along the incline always, an angle being the angle of the incline, and M1G cosine 30, and normal force on the surface of incline. To find the acceleration of the system, we can look at the whole system. And here we will see that these T's are in two opposite directions and they will cancel each other. Following question, you can directly jump there. If we are looking at the whole system, we do not have to consider the tension in the rope because they will always be canceling each other. Always we will have tension in two opposite directions along a rope. But let's write down everything for now to understand. So we'll be using total F is equal to M total times A. And this direction, this rotational direction is positive again. Over here I have Mg, M2G positive. T here negative because in opposite direction to positive. If I come to there, T here is positive. And M1G sine 30 is negative. For M1, moving in this direction, This is the positive direction. So 1t is negative, 1t is positive. It's already shown us that they will cancel each other. So let's write down our total forces. M2g positive minus t plus t minus m1g sine 30. No friction, no more forces in here. Will be equal to m total, m1 plus m2 times a. And this will give me the value of a. T's cancel each other. What I am left with m2g minus m1g sine 30. I could say that here, but 30 anyways. Is equal to m1 plus m2 times a. And let's put the values now. Next time when we're solving these type of questions, when we're considering the whole system, ignore tension in the rope and write down the other forces, m2g minus m1g sine 30 you will be left with anyways. And once we get to find the tension, then we're going to separate the system, and then we'll be able to find the tension. We'll get there. In this question we'll have to find tension as well. So let's put the values. M1 is 8 kilogram. Oh, this is M2, sorry. 22 kilogram is M2 times 9.8 meters per second squared minus M1 is 8 kilogram times 9.8 meters per second squared times sine 30 is equal to M1 plus M2. So 8 plus 22 kilograms times A. And from here we can get A by dividing this. So A will be equal to, let me put down everything, 22 kilograms times 9.8 meters per second squared minus 8 kilograms times 9.8 meters per second squared times sine 30 divided by 22 plus 8, 30 kilograms. And this will give us A as meters per second squared. Everything is in MKS units. I'm safe there, and my answer should be correct. Please again check the answer as a practice, and also check if I have any calculations there. The acceleration from here should be 5.88 meters per second squared. 5.9, 6 would be all acceptable answers. So this is A of the total system. Each separate mass, again, similar to the masses we were pushing together, will have the same acceleration. And then to solve for T, we're going to separate this system in two and find what is T using the value of acceleration we got in here. And let me do that in there, in this part. You can see that. So I'm going to separate M2 in here to solve. I choose M2 because it's easier for me. This part has sine and cosine. I don't have to deal with that. So I'm going to draw M2 separate in here. I have downward direction M2G, and I have upward direction T, and this direction is my positive direction of choice, not changing it. And I got A for M2 to be 5.9. Let's do the more precise one. 5.88 meters per second squared. And I'm going to find T. I know M2G, 22 kilograms times 9.8 meters per second squared. I can get to T. So total force for this M2G will be in this direction. I'm going to write down total force, and it will be equal to total F2, should I say that? Let's say total F2, it won't be confusing here. Will be equal to M2 times A. So total force acting on M2 is equal to M2 times A. And total force acting on M2 is M2G is positive and T is negative in here. So it will be M2G minus T is equal to M2A. And from here we can solve for T. Take T to this side as positive, this will become this side as negative, and T will be equal to, so M2G minus M2A is equal to T. Will give us the value of T. Enter the values and get T. The answer should be 86.24. So 86.24 Newton. 86.2 Newton. This is T. And the same would go for M1. I would really encourage you to go find T for M1 using the M1 system. It will be simply T minus M1G sine theta. And make sure that they are equal to each other. This will help you practice, and again, check that if this question is solved correctly. Now we have a part B to this question, and we are done with this lecture. I am going to delete all these. Let's put the tension. Oh, it will change. Never mind. Everything will change in this part because it's asking us what happens if there's a frictional force. We'll be calculating the same things in the case of there is friction. I'm going to delete this. I'm going to put B. And it says if, that made it to you. So it will be better English. If we can only find the question. So B says find the acceleration of each block and tension in the core if the coefficient of friction, kinetic friction, is 0.2. So it's given us now there is a friction and the coefficient of kinetic friction is equal to 0.2. Now what is acceleration and T? Everything will change now? Yes, because we're going to have an additional force to the left. And I'm going to show it with the red. We are going to have a frictional force, kinetic frictional force acting on M1, and let's call this Fk1. Now the whole system is the same. It will also be moving in this direction because this is still very large, but this frictional force in some cases could be strong enough to stop the motion. When would that happen? If mg on this side will be equal to Fk1 plus m1g sine theta. If m2g is larger, it will be pulled in the same direction, which what will happen here, but there could be other cases. I wouldn't though ask you to decide the direction of motion. It could be confusing, but there could be a lot of nice questions coming out of that. So the direction of motion will be the same. We have the same m2g pulling in this direction. This will be a positive direction. Only A will be different now, because there's another force against the motion, and this will change the total F of the system, which changes the area expected, of course. What we use is information for solution is the same thing. Newton's second law, total F is equal to m total times A. Now I'm directly jump into the forces because we decided direction of motion, positive direction is the same. This Fk will be negative. That's all I need to decide now. And I'm going to write down forces positive. And 2g, I'm also gonna not consider t's because they will cancel each other anyways for the whole system. I'm not taking any t. So I have m2g positive minus m1g sine 30 minus fk1, kinetic frictional force on m1 is equal to m1 plus m2 times a. And this will give me a different value of a. Let's write this down for A. A is equal to m2g minus m1g sine 30 minus f, k in the kinetic 1, divided by m1 plus m2. I don't really need to actually, but I'm going to put all the values as well. So m2 is 22 kilograms times 9.8 meters per second squared, g, minus m1, 8 kilogram times 9.8 meters per second squared times sine 30. Oh well, I'll do this so it will fit nicely and you can see it. Alright, this is fine. Let's move this to the left a little bit so we can solve it all in here. So A is equal to 22 kilograms times 9.8 meters per second squared minus 8 kilograms M1, 9.8 meters per second squared G times sine 30 minus FK1. I'm going to put FK1 in there too. But let's calculate it in here first. What is FK1 equal to? Is equal to mu K times N on M1. And N is always equal to M1 cosine theta in here. M1G cosine theta. Unless there are other forces acting perpendicular to the surface. So FK1 is equal to then mu K times M1G times cosine 30. And I'm going to put these values in there as well. So mu K is 0.2, M1G 8 kilograms times 9.8 meters per second squared times cosine 30. Get these numbers divided by M1 plus M2 again, 8 kilograms plus 22 kilograms will give you a value of A. It should give you a value of A. Let me see here. I'm gonna have to move on because it's already 46 minutes. And A should be 5.88 meters per second squared. Now I am gonna solve a similar question in the classroom, maybe Friday probably, but the second part I'm gonna leave to you to solve, so this will not be very, very large. Lecture again. But what you have to do in second part to find T, separate M2G again. You have M2G here. You have T pulling up. This is positive direction. Everything is the same as an A. You'll get T different though because now you have a different A. A is now equal to 5.88 meters per second squared. Go ahead and do this. You should find T as, let me give you the value as well. Oh, I gave you the wrong A. Sorry about this. Stay from part A. Okay, sorry, that should change. Alright, let me find A in here. So T should be 96.14 newtons, but the value of A, I am missing 5.43. Sorry about that. Slightly different, but different. So the A is 5.43 now. 5.4 is good. Use it in there. This was from part A. Sorry about that. And find T. Simply you'll have my mg minus T is equal to ma, m2a, and get T from there. See you in class.